Welcome. Let's try to write down some finite geometry in the style of Euclid, how Euclid would do that. It's a fantastic book from 300 BC, which is still readable today. It's amazing, after 2,300 years. It has a structure which went into all of mathematics, right? That you have definitions, you have some postulates, and you have some axioms, and you have propositions and theorems. It's an amazing achievement, not only for the subject, but for the way how to think and how to do science by proving things. As space, I just take a finite abstract simplicity complex, a finite set of non-empty sets closed under the operation of taking finite non-empty subsets. I just call it space, and the dimension is an important quantity. The dimension of a set is just the cardinality of the set minus 1. And then the dimension of the whole space is the maximal dimension which can occur. Now, really in the style of Euclid is a point that has no part, right? The points are just elements in G which have dimension 0. Edges are elements which have dimension 1. Triangles, these are elements of dimension 2. What is very crucial is to look at the star of an element. A star of an element is everything which contains X. So that's the star. It's kind of, think about it as an open set, an open ball, the smallest open ball. It's a basis for a topology, Alexandrov topology. And then we can also define the ball, which is the closure. In the postulates, I was putting some things what you can do with sets. You can, take the union, you can take the intersection, you can take the set of subsets, you can build a Cartesian product. It's kind of what we would say today. It's a topos, kind of the structure of when two of these spaces are equivalent. You call them isomorphic. But the closure is kind of here coming in for the unit ball. And then you can take away the interior of the unit ball and you get the sphere. That's the unit sphere. It's a very important notion. We don't have lines and planes, etc. in these simplicity complexes, right? So these are finite set of sets, but we have spheres. So it's something which comes from finite geometry. Also, spheres play an important role. Circles, in particular, if you look at Euclid. We can also look at quantities like length or area or angle, what Euclid looked at. So here we have not yet calculus. We don't really go into calculus. We also don't go into linear algebra. So all of this book 1, right, of geometry, we just look at geometry itself. And but some things we have to talk about something. We have to have some theorems, and you need some quantities. And one of the things you can do is define an energy for every set, which is -1 to the dimension of the set. So points have energy 1, edges have energy -1, triangles have energy 1, tetrahedra have energy -1, etc. It's just the sum of these energies is now the Euler characteristic, which is one of the most important notions in all of mathematics, because most important theorems are about Euler characteristic, like Gauss-Bonnet. Even more exciting is higher characteristic. So this is something which is not so well studied yet, but it has been started in the 50s. It's the energy of clusters in G. So we have M sets which all intersect. You take the product of all these energies, and that's a higher energy. So it's in the case m equal to 2, it's an Ising type energy, an interaction energy. And then a last thing which is kind of coming in is some algebra, which is the join operation, defines a monoid structure of these spaces, so you can add spaces. And the join is a nice operation which behaves nice. It's very useful for constructions, and structure which naturally comes in when you look at finite geometry. In particular, I didn't write this down yet here. I don't have space for everything, but the unit sphere, for example, decomposes as a join of a stable and unstable part. So we have here, I think I mentioned kind of the postulates, I mentioned the definitions. Whether you call it definition or postulate or axiom, it doesn't matter. What you establish are the rules of the game and the language which you use to describe this game. And now we can start to prove results. So maybe the first one is something about topology. I love finite topology. I mean, finite topology is something very, very established. Topology is very established in mathematics. It's a set of sets, which is, arbitrary unions are there, finite intersections are there. Here in the finite case, we don't have arbitrary, I mean, we have always finite. So we have no infinity axiom coming in. So it's essentially kind of the, an axiom system which has a chance to be completely consistent. And then, so this is a finite topology. So the empty set, which is the void, is, open and closed also. So it's also a space. So if you have a space, you have a topology. It's a non-Hausdorff topology, but it has the right properties. It gives you the right connectivity properties, the right topological, the topological dimension, for example, of a set is really what you would, consider to be the dimension. It's the maximal dimension. Now, this is already kind of starting to become interesting. We have this valuation property for Euler characteristic, which is obvious for Euler characteristic, because what you do if you have two sets, and so there's this inclusion-exclusion principle, which just counting, and you are super counting. So this is a valuation property, which not so obvious is for higher characteristic. For higher characteristic, it only holds for open sets. So if you take closed sets, for example, it's not. Now that's pretty clear from the definition. It's a nice, but it's important that you can describe in the join. You can describe the unit sphere. That's for induction important. When you are going to prove something, what you can do is you can use the sphere to get to a smaller simplicial complex. And the smaller simplicial complex usually has assumed to have some properties, like in this case we assume that we have just kind of a dimension stratification of the dimension, so that the unit sphere has dimension 1 less, and also the Euler characteristic should be fixed. And in this case we really have a nice theorem. This is kind of, highly non-trivial already. And also here, this is also kind of just pretty much from the definition. You can prove that nicely using calculus when introducing simplex generating function, but you can also just write it down. For now, I don't want to get into calculus and not get into linear algebra, and which is the if you add 1, if you take the join with 1, which is kind of a pyramid extension, cone extension, then it always has Euler characteristic 1. Now, this is also a nice property, also very, very general. This is true for every simplicial complex, every open set, so that you actually can describe the nth characteristic. And the reason is that all these sets here really, when you are in Ux, all of them intersect. They contain X by definition. That's kind of a nice, kind of a useful property. This is not so easy. Actually, I mentioned this 2 years ago in a theorem, but I actually didn't prove it there. It's a little bit messy, and I still want to see kind of a nice proof of this, which is not crazy. So for m equal to 1, it's obvious. That's just a valuation property because the open set and the boundary, they complement each other to the closed set. So in the case m equal to 1, this is just the valuation property. But for the higher thing, this is not so easy. And it's also wrong if you take here an arbitrary open set. For example, you take the union of two open sets, two stars, then it's already can become false. This is just one star. It's kind of a formula for a nice local valuation property. And this can be useful in this context. These are already quite highly non-trivial results. This is a one-point green function identity, and this is, I call this the sphere formula. This is the k-point sphere formula. That's kind of the the most sophisticated things which I kind of have seen. Especially I started here with a 2-point, k is equal to 2, then you have the intersection here. So this is then actually this is related to matrices, unimodular matrices. But again, we don't do any linear algebra here. And this is nice. I call this, that's why I got into that again. These are Dane-Somerville spaces. These are spaces which have lots of more symmetry. And one of the symmetries is that the nth characteristic is 0 in odd dimension. So it's kind of one of these Dane-Somerville symmetries. So they are, behave like manifolds and have lots and lots of properties which manifolds have. And I talked about this last time. But that's it for today. Just a little bit of an attempt to go back to Euclid. How would Euclid have done finite geometry?